Moving along here to section 1.3, this is new functions from old functions. There's really two parts to this. The first part is going to be the transformations of functions. The second part is going to be combining functions. In this video, we will look at the transformations of functions. And the first type of transformations we want to look at is vertical and horizontal shifts. So let's start with the vertical shifts. And let's start with the function. Let's say y equals some function f of x. And we'll just make it the simple function f of x equals x squared. So we know what the graph of this looks like. If we draw a graph of f of x equals x squared, well, we just have this parabola opening up with a vertex at the origin. Well, we're going to vertically shift this graph by just adding numbers on to the end. So, for example, if we look at y equals f of x plus 2, in other words, y equals x squared plus 2, that's going to shift the graph up 2 units. And so we would move up 2 units. We would have the exact same graph copied, only shifted up 2 units. If we look at a graph of y equals f of x, say, minus 1, that would be y equals f of x is x squared minus 1. That's going to shift the graph down 1 unit because of the negative. And so the graph there, if we draw it on the same set of axes, would be shifted down 1 unit. It would look like this. So you can see how the vertical shifts are achieved by just adding or subtracting numbers onto the end of the function. Now let's take a look at horizontal shifting. Here we start with the same function, y equals f of x, which is equal to x squared. Again, we'll just draw that graph in. Here's y equals x squared. Now let's go ahead and switch this, or transform this. Let's let y equal f of x plus 2. Now this is different than f of x, close parentheses, plus 2. Here we are adding 2 to our variable and then applying the function. So in other words, we're going to add 2 first and then square it. What's this going to do? It's actually going to shift to the left. Shift to the left 2 units. And why is that? Well, think about what value of x would make this quantity 0. The value of x that would make this quantity 0 is negative 2. So I'm going to have to move 2 units to the left to get this vertex point to be 0. So the graph of y equals f of x minus 2 is going to look, f of x plus 2 quantity squared is going to be shifted 2 units to the left. It's going to look like that. Conversely, if we look at a graph of, say, y equals f of x minus 1, so again, here we're subtracting 1 from x first and then squaring it, this is going to shift it to the right. It's going to shift it to the right 1 unit. And we can see that because, again, a positive 1 would make this quantity 0. So I have to move to the right 1 unit to a positive 1 to get that vertex point of 1 comma 0. So here's my graph shifted 1 unit to the right. Let's just look at another example here. We have y equals the square root of x. This is a program called WinPlot, and you can get this program by just typing in WinPlot into Google, and it'll probably be the first thing that comes up, W-I-N-P-L-O-T. It's a free graphing program, very good software actually. So here's y equals the square root of x. You can see it's this graph here in blue. Notice the domain of this is 0 to infinity because we can't take the square root of a negative number. Now let's go ahead and put in a new function on the same graph. So let's say we want to take the square root of x plus 2. Well, now we're adding 2 to the end of our function, so that should shift it up 2 units, and it does. It takes that original blue function and shifts it up 2 units. What if we did y equals the square root of x plus 2 inside the parentheses? So we're first going to add 2 to x and then take the square root. This should shift it to the left 2 units from the original blue function, and it does. What if we did a combination of the two things, and we did, say, y equals the square root of x plus 2 minus 1. Well, the x plus 2 inside the parentheses, inside the square root, is going to be to the left 2 units and then down 1 unit for the minus 1 at the end of our function. So it should be the blue function to the left 2, like this yellow function here, and then down 1. Let's see. Yeah, there it is there in black. Alright, so that's what those look like. And that's how we can visually see graphically the horizontal and vertical shifting. And just so we can see, we have different notation to put it into the computer. Here was our notation here. Y equals the square root of x was our first function. Then we did y equals the square root of x plus 2, which shifted it 2 units to the left. Then we did y equals, actually that's not right, our second function was y equals the square root of x plus 2 after the square root. So it looked like this. That was our second one we did. Then we did the square root of x plus 2. That was our shift 2 units to the left. And finally we did the square root of x plus 2 minus 1. So that's how it would look notationally writing out the formulas. Next thing we want to look at in transforming functions is vertical and horizontal stretching and reflection. So let's just start off with a function y equals f of x. And we're going to look at the different cases. These are all in your book on page 39. The first thing is we have a stretch. If we take y equals c times f of x, so some number times f of x, and that number being bigger than 1, then that will stretch the original graph of y equals f of x vertically by a factor of c. Now, if we take a number less than 1, so c is bigger than 1, we look at something like y equals 1 over c times f of x. So say if c is equal to 2, we're multiplying our function by 1/2, then that's going to compress the graph of y equals f of x vertically by a factor of c. So it'll only be half as tall as it was previously if c was equal to 2, for example. If we have y equals f of c times x, we take some constant c times the variable first and then apply the function. That'll compress the graph horizontally by a factor of c. And if we have y equals f of x over c, in other words, we take our variable, divide it by some c that's bigger than 1, that'll stretch our graph of y equals f of x horizontally, is what that says there, horizontally, by a factor of c. Finally, y equals negative f of x reflects the graph of y equals f of x over the x-axis. And if we look at y equals f of negative x, that will reflect the graph of y equals f of x over the y-axis. So, again, these are all just listed out in your book for you on page 39. Let's look at an example. Let's take a look at number 5 out of your book. If you look in your book on number 5, you see this graph here, and then there's 4 shifts that we want to do, 4 graphs we want to make. The first one is f of 2x. So if you look back at our list here of situations for horizontal and vertical stretches, we're at this situation right here. F of a number times x, that number being bigger than 1, that's going to compress the graph horizontally by a factor of c. So what we're going to do is we're going to take this graph, we're going to shift it, compress it horizontally by a factor of c. Now, for example, when x is equal to 0, well, 2 times 0 is 0, so f of 0 is going to be the same as f of 2 times 0, which is going to be 1. But this point, so f of 1 is equal to 2. F of 1 is equal to 2. Well, that means if I put x equals 1/2 in, well, 2 times 1/2 is 1, so that'll get mapped up to 2. So instead of this point at 1, 2, we're going to have a 1/2, 2. This point at 2, 1 is going to be backed up to 1, 1. Because again, if I put 1 in for x, 2 times 1 is 2. F of 2 is supposed to be 1 right here. So this gets backed up then to half. This is at 3, so it gets backed up to 1.5. This point here at 4, -1 gets backed up to 2, -1. This point at 5, -1/2 gets backed up to 2.5, -1/2. And finally, this point at 6, 0 gets backed up to 3, 0. So we've taken this original graph here and we have compressed it horizontally by a factor of 2. Basically we've made it half as wide. How about part B, where we're looking at y equals f of 1/2 x? Well, here we're in the situation where we have f of x over a number bigger than 1. So we're in this situation right here. This is going to stretch the graph horizontally by a factor of c, in this case c being equal to 2. So we're going to stretch things horizontally by a factor of 2. In other words, we're still going to have this 0, 0 point, but instead of 1, 2, we're going to be at 2, 2. So we're going to be up here. Instead of 2, 1, we're going to be at 4, 1. So we're going to be right here. Instead of 3, 0, we're going to be at 6, 0. We're not going to be able to draw all the graph. We can draw the first part of it. It's going to look like this. So that's this first part. It's this section right here up till 3, stretched out horizontally by a factor of 2. Alright, part C then asks us to look at y equals f of negative x. And if we look back at our list here, f of negative x reflects the graph over the y-axis. So we're going to flip this thing over the y-axis, so we're going to have to maybe extend this graph off to the left. And so flipping this over the y-axis, think about it, if you put a positive 1 in, well, We're only defined on the original graph for values from x equals 0 to 6. So if I were going to put a negative 1 in to x in this problem right here, I would have a negative, negative 1, which is a positive 1. What is f of positive 1? Well, f of positive 1 is at 2. So f of negative, negative 1 is also going to map up to 2. In other words, there's our reflection over that y-axis. So we have, instead of the point 2 comma 1, we'd have the point negative 2 comma 1. Instead of the point 3 0, we'd have the point negative 3 0. Instead of the point 4 negative 1, we'd have the point negative 4 negative 1. Instead of the point 5 negative 1 half, we'd have negative 5 negative 1 half. And instead of the point 6 comma 0, we would have the point negative 6 comma 0. So this is what our graph's going to look like. It starts at the same point right here, and connecting those dots, then we see the graph of y equals f of negative x. Finally, then, in part D, we want y equals the negative f of negative x. That's negating the last graph. So let's do this one in orange. The negative of the graph we had in part C. Well, if you negate a graph, you take the negative of a function. That's the situation right here. That's going to reflect it over the x-axis. So basically we're going to take this last graph in green and we're going to reflect everything over the x-axis. So instead of 0, 1, we're going to be at 0, negative 1. Instead of negative 1, positive 2, we'll be at negative 1, negative 2. Instead of negative 2, 1, we'll be at negative 2, negative 1. Instead of negative 3, 0, we'll be at negative 3, 0. Well, that's the same point because it's on the x-axis. Instead of negative 4, negative 1, we'll be at negative 4, positive 1. Instead of negative 5, negative 1 half, we'll be at negative 5, positive 1 half. And negative 6, 0 is the same. So here is our graph of negative f of negative x. Taking a look at number 7, applying some of the things that we've done here, let's see if we can transform from this function. The function given in number 7 is f of x equals the square root of 3x minus x squared. Its graph is this graph in blue. We want to apply transformations to get the formula for this function shown here. Now you can see the similarities here. This is a half of a circle that has a diameter of 3 and a height here of 1.5, so a radius also. So it's just the top half of a circle of radius 1.5. Well, here we have the bottom half of a circle of radius 1.5. The diameter across here is 3, and we go from a negative 1 to a negative 2.5, so we have a radius of 1.5 as well. So how do we get from here to here? Well, we're going to take f of x, and the first thing we'll do is flip it over the y-axis. So we'll flip it over the y-axis to get this graph here. That goes to negative 3 and still tops out there at 1.5. So in green here, that's going to be f of, let's see, to flip it over the y-axis, remember we take f of negative x. So we're going to replace x with a negative x wherever we see it. Alright, let's simplify this. Well, 3 times a negative x, that's going to be negative 3x. And a negative, well, negative x quantity squared is a positive x squared, so we have this function right here. Alright, next thing we want to do is flip it then over the x-axis. So get it down here, so we're going to do this. So now it has a half of a circle that's the bottom half, so it's going down to negative 1.5. Well, how do you negate that? Well, we're going to take the negative of what we had previously. So we're going to take the negative of f of negative x, which is the negative of the square root of negative 3x minus x squared, and we can just leave it like that. Finally, to get from this purple graph here to this graph that we're looking for, we have to subtract 1 from f of x, or from this original function here, or from this purple function, I should say. So we're going to take the negative of f of negative x and subtract 1. Remember that minus 1 will be a vertical shift down. So that would be the negative square root of the negative 3x minus x squared function, and then minus 1. Let's see if we can verify that. So let's start by looking at the original function, y equals the square root of 3x minus x squared. And you can see the original graph that we had. It's the top half of a circle of radius 1.5. Now, what do we want to do here? We want to put in a new function and see if the new formula we had is correct. What was the new formula we had? Well, it was the negative of the square root of negative 3x minus x squared, and then that minus 1. So let's put that in right here. We have the negative of the square root of negative 3x minus x squared, and then that minus 1, and what do we get? We get the exact graph that we had before, that we wanted to get. We have the bottom half of that circle, and it's flipped over the y-axis, flipped over the x-axis, and shifted down 1 unit. So that is the correct formula. And that will conclude the first part of the lecture and examples from section 1.3. The next part will deal with combining functions.